Okay, let's look at this idea of integration using substitution, and the idea is we want to turn our integral into one of the standard forms, and then we know how to integrate it. So what are our standard integrals? The ones that do appear on our reference sheet. We get this one, so that's our basic one for add 1 to the power over the power, that idea, if we can put it in that format of derivative times some function to the power of n. The sine ones there, of course, as is the cosine and the sec squared, again written in the form derivative times the function. For exponential, that's the one we see, f dash x e to the function x, and log, derivative over function. They also on the reference sheet have this one, which reminds us that, hey, when we integrate an exponential where the base is not e, we do it the same way, but we divide by the natural log of the base. And the inverse trig ones, so inverse sines there, inverse tans there. Interestingly, they don't say that that second last one is also minus the inverse cos, but hopefully that's something we just remember we could do that. So we want to rewrite this one, and we're given the substitution u equals 4x squared plus 8x minus 7. Now, in extension 1, they generally tell you which substitution to use, which can be good, it can be bad. It's good from the point of view that you don't have to think about it, oh, that's the substitution I'm going to use, but it's bad from the point of view that it ties your hands into what you're going to do. There's u, which is the bottom of the fraction. Now, had they not given me the substitution, then what I'm looking for basically is, well, what's causing me the problem here? And the problem is that if I was to change this into index form, it would become power of negative 1. And if we add 1 to the power, we'll get power of 0, but then put it over 0, that's not going to work. So I know there's something else happening here. I'll make the denominator the substitution. That means the derivative becomes 8x plus 8, and on the top of the fraction we have a multiple of the derivative. It's 1/8 of the derivative. That means I can rewrite this as 1/8 of du on u. There it is in standard form, so we know, oh well, that's the log of u. Then we substitute back in. That's a basic idea of integration by substitution. So I see this one. Again, they've given me it, but here, what's going to cause the problem? It's probably going to be the thing that is to the power there. So the log x is what I'm generally going to go with. dx on x, yep, I've got that as well. I can change that now to just du on u cubed, which is of course u to the negative 3, add 1 to the power over the power, substitute back in. Okay, let's look at this HSC one. They told us to use the substitution u equals 1 minus x for this one. So if u is 1 minus x, then du is minus dx, but it's a complete substitution. These limits are with respect to x, but I'm about to change it with respect to u. I need to change those limits as well. So when x equals negative 3, u is 4, and when x is 0, u is 1. Now I can do a complete substitution. I end up with minus 1 minus u on root u to u, going from 4 to 1. Okay, well, I'll swap the limits around and make it positive, so it's 1 to 4, and this fraction I'll split into two things that I can now integrate. I have 1 on root u, which I have to integrate, and also minus root u. Now that 1 on root u, sure, I could change that to u to the negative half, add 1 to the power over the power. But it's one of those ones that's well worth remembering because we see it a lot. So 1 over root u will be 2 root u. Now it's not on the standard integral sheet, but as I say, it's one well worth remembering. So then you don't have to go to the bother of, oh, let's put it into index form, add 1 to the power over the power, and then convert back. The root u, well, that's u to the half. So again, if I add 1 to the power, I'll get 3 on 2, which is u root u, and I'll get 2/3 out the front. If you find you're making mistakes, then of course put it into index form and do it that way. If that's what's causing the problem, trying to do too much in your head without working out, well then put the working out. Substitute in 4, substitute in 1, negative 8 on 3. Okay. U equals cos squared x for this one. So if u equals cos squared x, du is minus 2 cos x sine x. But I notice in the integral I've got a sine 2x. So it makes sense to change this 2 cos x sine x to sine 2x. And it allows a straight substitution in. Again, I've got to work out those limits. So when x equals 0, u is 1. When x is pi on 4, u is a half. I end up with u on 4 plus u, which is a log function. I've got derivative on the function. So log of 4 plus u. You'll notice I didn't bother with the absolute value signs on this one because it's a definite integral. I know with those limits I'm going to end up with positive numbers anyway. It doesn't matter. If you put them in, don't put them in on one like this, it doesn't matter. I end up with the log of 10 on 9 once I play around with those log laws, combine it into one log. This time they've given me the substitution in terms of u rather than in terms of x. X equals u squared minus 1. Well, if x equals u squared minus 1, why did they give me that substitution? Because essentially what it means is u is the square root of x plus 1, which is the denominator in this question. Dx becomes 2u du. The advantage, I guess, of doing it this way is I can just substitute straight in for dx. I don't have to do any manipulation to get it in there. And let's change those limits around as well. So substituting all that in, nicely those u's end up cancelling. So I'm just integrating u squared minus 1, which of course is add 1 to the power over the power. Substitute in, we get 8/3. There's just one thing we have to be careful with. When we change it round and make it x equals function u, we have to make sure that the substitution is consistent with the actual domain of the function itself. What do I mean by that? You see, why couldn't I, if x is u squared minus 1, why couldn't I have said, well, u is minus the square root of x plus 1? That would still be correct. Now when I substitute in to get the u becomes negative 1 when x equals 0, and u becomes negative 2 when x equals 3. If I was to now do the integration using all that information, I end up with an answer of minus 8/3. But of course that's wrong. Remember, the answer was 8/3. What is it? What we've just found is this integral, where the denominator was minus the square root of x plus 1, not the square root of x plus 1. So it's just something to keep an eye on there. Generally, just make it match what you're going to end up substituting in and you're going to be okay. U is e to the x plus 2e to the minus x, but by considering u squared, find this one. Okay. Well, there's u. Differentiator, I get du. They've said by considering u squared, so let's work out what that is and see what they're getting at. And when I square u, okay, it's sort of highlighting, it's going to have something to do with the bottom of the fraction here. Not quite the same, but there's the e to the 2x and 4e to the minus 2x. Ooh, not quite the same. So how do I make it the same? Because essentially that's what I want to do. I'm going to substitute u squared. Well, to make it the same, if I was to get every term in the denominator here, and what am I doing? Dividing by e to the 2x. Then I will get the same as that u squared. Right? So the 4 becomes, well, I'm dividing by e to the 2x, so that's e to the minus 2x. The 8, e to the 2x now just becomes 8. And the plus e to the 2x. Again, you might look at this, hang on, it's 4, not 8, but that's all right. I can add or subtract a constant number and still get it. Of course, I've got to do the same to the numerator as well. The numerator now becomes e to the x minus 2, e to the minus x, which nicely is the du. So I've got du on u squared plus 4. That's a standard integral. There's our inverse tan. So now that's 1/2 the inverse tan of u on 2. Now substitute the u back in and we have our answer. Okay, so 12D, 12E, playing with integration by substitution.